Welcome! You most likely just learned how to do U substitution and use U substitution with indefinite integrals. Today we are going to focus on definite integrals where we need U substitution. The steps are very similar to what we did yesterday. We're going to start off by choosing what our U expression is. We're going to take the derivative of that U equation, solve for dx, plug that back into the original problem along with U. We're going to find our antiderivative, and today we're not worrying about indefinite, so you will not need to add a plus c in. Remember, plus c is always going to cancel when you have lower and upper limits of integration. And then you can plug the u expression back into your antiderivative and evaluate your antiderivative. But I'm going to show two different methods that you can use. So one method has you plugging u back in and applying your fundamental theorem of calculus. The other method actually has you change your limits of integration so that everything is in terms of u, and then you can skip that step of substituting u back in. All right, so take a look at example number 6. So we've got the integral from 0 to 4 of the square root of 2x plus 1 dx. And what we're being asked to do is integrate this. Obviously, that's a function within a function. I can't just reverse a power rule, for example. So I'm going to start by identifying u as 2x plus 1. And I know that if I'm going to replace this expression with u, I also want this to be a du. So to create a du, I'm going to differentiate this equation over here. So the derivative of u is 1 du dx. Derivative of 2x plus 1 is 2 dx dx. Multiply both sides by dx. My dx's cancel. And I'm going to solve for dx so that I can substitute in here. So du over 2 equals dx. So I've got two things to substitute in. U is taking the place of 2x plus 1 in here, and du over 2 is taking the place of dx. So here's my u. In place of dx, we have du over 2. So this is going to be my integral from 0 to 4. I'm going to rewrite that as u to the 1/2. I am going to move this 2 to the outside as a 1/2 du. And I'm ready to reverse my power rule. So when I take the antiderivative, or when I integrate this, I know I'm going to bump up my power from u to the 1/2 to u to the 3/2. I'm going to divide by 3/2, which is the same as multiplying by 2/3. I'm going to close that off. Now, normally I'd add a plus c if it's an indefinite integral, but this is a definite integral, which means I am going to have to evaluate at 4, evaluate at 0, and subtract those expressions, or in this case, those numeric values. If you want to, you can actually clean this up too. So my 2's will cancel. So really I have 1/3 times u to the 3/2 evaluated from 4 to 0. Now here's the deal. The 4 and the 0 are x values from my original problem. I can't substitute x values into this u. So what I'm going to do, I'm going to plug the u expression back in. So the u expression really took the place of 2x plus 1. And that is the fifth step here, plugging the u expression back into your antiderivative before you evaluate using the fundamental theorem of calculus. So that 1/3 carries down out here. Now I am ready to substitute numbers in. So I'm going to substitute 4 in here. So 2 times 4 plus 1 to the 3/2 minus, and I'm going to substitute 0 in. 2, that should be closed off there. 2 times 0 plus 1 to the 3/2. Let's clean that up a little bit more. So 2 times 4 is 8, plus 1 is 9 to the 3/2 power. 0 plus 1 is 1 to the 3/2 power. So 9 to the 3/2, that's the square root of 9, which is 3, cubed is 27. The square root of 1 is 1, cubed is 1. So 27 minus 1 is 26, times 1/3 would be 26/3. So that would be my answer to the question of what is the area under this curve from 0 to 4? And that should be a numeric answer because we have defined limits of integration. So this is method 1, and it is very similar to what you learned with indefinite integrals. I'm going to show you an alternate method. This is method 2. And the main difference, we're going to start it out the same way. I'm going to substitute in the exact same u expression, the exact same dx expression, but my limits of integration go from 0 to 4, and that requires, those are x values, that requires that I switch back to x in order to substitute those in. Well, what if I changed my limits from x values over to u values? So this is method 2. I'm starting with the same exact u expression, 2x plus 1, du dx equals 2 dx dx. Dx is canceled, divide by 2. If this is looking familiar, it's because we just did it right here. And I'm going to substitute my u in here for 2x plus 1 and my du over 2 out here. So this is where I'm going to take another step. And instead of carrying down my 4 and my 0, those are x values. Now, when x equals 4, what is u? Well, I'm going to substitute 4 in here to find u. So 2 times 4 plus 1 is 9. So that means my new upper limit in terms of u is 9. And then I'm going to find when x is 0, what is u? So when x is 0, u is 2 times 0 plus 1, which is 1. And now that everything is in terms of u, I never have to go back to x. So I'm going to carry down this integral from 1 to 9. I'm going to pull this 2 out as a 1/2. I'm going to rewrite this as u to the 1/2. And I am ready to apply my fundamental theorem of calculus. So my 1/2 carries down. I'm going to reverse my power rule. So that's u to the 3/2 divided by 3/2, which is the same as multiplying by 2/3. And I'm going to integrate from 1 to 9. And you do not need to substitute that 2x plus 1 in. We can actually start substituting the 9 and the 1 in. If you'd like, because there's no other terms here, you can actually combine these constant numbers out here. So you can pull that 1/3 way out in the front. If you had any other terms being added or subtracted in here, that is not an option. You'd have to keep that 2/3 attached to that u to the 3/2. And now I am ready to substitute in my 9, so 9 to the 3/2 minus 1 to the 3/2. This is starting to look a little familiar. 9 to the 3/2 minus 1 to the 3/2. In fact, when we calculated that 9 and 1, those were the values that we got in here. There was my 9, there was my 1. So we've got 1/3 times square root of 9 cubed is 27, square root of 1 cubed is 1, so we have 26 over 3. I will usually use this method, so switch everything over to u, but that is up to you. You can go back to x if you want to be more consistent with how we did our indefinite integrals. All right, thank you so much for listening. There will be a second video that shows 2 more examples, number 7 and number 8. Thank you so much.